Why humans will struggle on Mars. Did you know that if you were to stand on Mars right now, your bones would begin weakening immediately? Within months, your skeleton could lose 30% of its density, a biological crisis threatening both mobility and survival in the harsh Martian environment. Our bodies evolved for Earth's gravity and protective atmosphere, not the punishing conditions of the red planet. Space agencies have invested billions developing countermeasures against these devastating effects, yet fundamental challenges remain. This documentary examines the profound biological obstacles humans face on Mars, revealing the scientific realities that could determine whether we'll ever truly expand beyond our home planet. The allure of Mars. For millennia, Mars has held a special place in our collective imagination. Long before telescopes and space probes, ancient civilizations tracked its distinctive reddish glow as it wandered through the night sky. The Romans named it after their god of war, seeing something provocative in its blood-red appearance. But our modern fascination with the red planet runs deeper than mere astronomical curiosity. Of all the planets in our solar system, Mars stands out as tantalizingly Earth-like. When viewed through even basic telescopes, Mars reveals polar ice caps that expand and contract with the seasons, suggesting familiar weather patterns. Its day lasts just 40 minutes longer than Earth's, giving it a daily rhythm remarkably similar to our own. These surface-level similarities have fueled centuries of speculation about what, or who, might exist on our planetary neighbor. The late 19th century marked a pivotal moment in our Mars obsession. Imagine an astronomer like Giovanni Schiaparelli peering through his telescope in 1877, sketching what he called canali on the Martian surface. Though he meant natural channels, the mistranslation to canals in English implied artificial construction. American astronomer Percival Lowell developed this idea, publishing maps showing elaborate canal networks that he believed irrigated a dying world. These visions, though inaccurate, planted the seeds for Mars as we conceptualize it today, a potentially habitable world. Science fiction authors transformed these scientific misconceptions into rich narratives. H.G. Wells' War of the Worlds introduced Martians as invaders, reflecting anxieties about imperialism. Ray Bradbury's The Martian Chronicles depicted Mars as an escape from a troubled Earth, establishing the planet as humanity's potential second home. Andy Weir's The Martian presented a scientifically grounded survival story that made Mars settlement feel achievable to modern audiences. This cultural backdrop has profoundly influenced our scientific approach to Mars. NASA's robotic explorers, from the Viking landers in the 1970s to today's Perseverance rover, have been designed to search for signs of habitability and life, carrying with them centuries of human speculation. Every discovery of ancient flowing water or organic compounds resonates deeply because it connects to our longing to find another world where we might belong. Today's images from Mars reveal a landscape simultaneously familiar and alien. The Jezero crater shows river deltas and lake beds reminiscent of Earth, despite being dry for billions of years. The famous blue sunset photographs capture an otherworldly beauty, our sun appearing as a diminished blue orb through Mars' dust-filled atmosphere. These images invite us in while reminding us of the planet's fundamental otherness. The contemporary push for human Mars missions builds on this relationship. SpaceX founder Elon Musk speaks of Mars as an insurance policy for humanity should Earth become uninhabitable. NASA's plans emphasize Mars as the logical next step after the Moon. Both frame Mars as a challenge surmountable with existing or near-future technology. Public enthusiasm for Mars exploration remains high across political and demographic lines, suggesting something about the red planet transcends ordinary divisions. This enthusiasm persists despite limited public understanding of Mars' hostile environment. Media presentations often highlight adventure aspects while downplaying extreme challenges. Artists' renderings show pressurized domes bathed in ambient light rather than harsh ultraviolet radiation. Discussions of agriculture emphasize successful experiments with simulated soil, but rarely mention the toxic perchlorates permeating the actual surface. The financial commitments behind Mars exploration reflect collective optimism. NASA's Mars 2020 mission cost approximately $2.7 billion, accepted as worthwhile. Private companies like SpaceX invest billions in developing Mars transport vehicles, while wealthy individuals volunteer millions for theoretical future tickets. This suggests a belief that the technical challenges are fundamentally engineering problems with straightforward solutions. But there's a crucial distinction between engineering challenges and biological realities. Spacecraft can be redesigned. The human body has evolved within specific parameters over millions of years. Our biological systems operate under fundamental assumptions. Consistent gravity at 9.8 meters per second squared, atmospheric pressure supporting our bodily fluids, a magnetic field deflecting harmful radiation, and precisely calibrated oxygen levels. The journey to Mars immediately begins dismantling these conditions. During the 6 to 9 month transit, astronauts would experience microgravity effects, bone density loss, muscle atrophy, vision changes, and cardiovascular strain. Upon arrival, Mars offers gravity at just 38% of Earth's, better than weightlessness, but far below what our bodies evolved to expect. The Martian atmosphere provides almost no protection against radiation. With no magnetosphere and atmosphere pressure less than 1% of Earth's, Mars offers minimal shielding against high-energy particles that damage DNA and cellular structures. An unprotected human would receive radiation doses dozens of times higher than safety limits on Earth, accelerating cancer risks and potentially causing cognitive impairment. Temperature variations would challenge our most sophisticated environmental systems. While Earth's habitable regions might vary by 40 degrees Celsius seasonally, Martian temperatures can swing by 100 degrees Celsius in a single day. Near the equator, daytime temperatures might reach 20 degrees Celsius before plummeting to minus 73 degrees Celsius at night. Maintaining habitable temperatures would require massive energy investments where failure means swift death. Perhaps most fundamentally, Mars lacks the basic atmosphere needed for human respiration. Composed of 95% carbon dioxide at less than 1% of Earth's pressure, Mars' atmosphere is actively hostile to human physiology. The low pressure would cause body fluids to boil at temperatures below our normal body temperature, while the carbon dioxide concentration would quickly lead to unconsciousness and death. Gravity's cruel math. Beyond the atmospheric dangers lurks a more insidious threat. The mathematical certainty of what happens when human physiology meets Martian gravity. Every bone, muscle, and organ in your body operates under the precise assumption of Earth's gravitational pull. On Mars, that fundamental force drops to just 38% of what your biology expects, triggering a cascade of deterioration that begins the moment you arrive. Evolution has meticulously calibrated human physiology to Earth's specific gravitational constant over millions of years. Our skeletal structure functions like a precisely engineered building, with load-bearing columns and support beams designed exactly for Earth's gravitational loads. Bones constantly remodel themselves through a delicate balance of osteoblasts, building new tissue, while osteoclasts break down old bone, a process gravity regulates. When that gravitational equation changes dramatically, the consequences are profound and predictable. Without the constant stress that Earth's gravity places on our skeletal system, our bodies begin to shed bone mass deemed unnecessary. The mechanism works with brutal efficiency. Calcium leaches from bones, weakening their structural integrity from the inside out. Data from astronaut studies on the International Space Station provides a troubling preview of what awaits Mars settlers. In microgravity environments, astronauts experience bone density decreases primarily in weight-bearing bones like the spine, hips, and legs, the very structures we rely on for mobility. The process begins almost immediately after arrival in reduced gravity, with measurable losses occurring within weeks. Mathematical models predicting physiological responses to Martian gravity suggest that without effective countermeasures, settlers could experience up to 30% bone density loss within just months of arrival. This deterioration is comparable to severe osteoporosis on Earth, a condition typically developing over decades in elderly individuals. On Mars, your skeleton could effectively age decades in mere months, potentially turning a 30-year-old colonist's bones into those of an 80-year-old. This calcium exodus creates a compounding problem. As calcium exits bone tissue, it enters the bloodstream, creating potential for kidney stones and cardiovascular calcification. Your body, operating on evolutionary programming designed for Earth, systematically dismantles its structural support system when the expected gravitational stress disappears. The same gravitational reduction that weakens bones simultaneously attacks our muscular system. Like our skeleton, muscles develop and maintain themselves in direct response to Earth's gravitational resistance. Each movement involves muscles working against gravity's pull. When that resistance decreases by nearly 2/3 on Mars, muscles rapidly waste away, following a predictable pattern. The largest muscles used for posture and locomotion experience the most significant atrophy, potentially leaving settlers struggling to perform basic physical tasks within months. This muscle loss further accelerates bone density deterioration, creating a downward spiral of physical decline. The cardiovascular system faces equally serious challenges in reduced gravity. On Earth, your circulatory system has evolved sophisticated mechanisms to ensure blood properly circulates against gravity's pull. These mechanisms include muscle tone in blood vessel walls, valves in veins, and heart adaptations, all calibrated to Earth's specific gravitational constant. In Mars' reduced gravity, fluid distribution fundamentally changes. Without Earth's pull, bodily fluids shift upward, with more blood collecting in the chest and head. This redistribution triggers physiological responses. The body perceives excess blood volume and eliminates fluid through increased urination. The heart, no longer working as hard against gravity, begins to decondition. Its muscle walls may thin while blood vessels lose elasticity, creating a particularly dangerous situation upon return to Earth, where astronauts often experience orthostatic intolerance, the inability to maintain blood pressure when standing. These effects would be cumulative and progressive with each passing month on Mars. The human body simply wasn't designed for variable gravity. It assumes Earth's specific 9.8 meters per square second and optimizes accordingly. Some physiological adaptations would eventually occur, but evolution works across generations, not within individual lifetimes. The first generations of Mars settlers would bear the full biological challenges without evolutionary adaptation. Their bodies would operate in an environment fundamentally mismatched to their biological design specifications. The implications extend beyond bone, muscle, and cardiovascular health. The vestibular system, responsible for balance and spatial orientation, relies on Earth's specific gravitational cues. In Mars' reduced gravity, settlers would likely experience persistent disorientation and coordination difficulties. The immune system, influenced by fluid distribution, might show altered responses to pathogens. Even reproduction and fetal development, processes optimized for Earth's gravity, raise serious questions about sustaining a Mars colony across generations. The biological responses to Martian gravity represent fundamental challenges to long-term human presence. While Hollywood often shows astronauts bouncing happily across the Martian surface, the biological reality would be a constant battle against your body's programming as it systematically breaks down in response to the altered gravitational equation. Human settlement of Mars isn't impossible, but we must approach it with clear recognition of the biological challenges involved. The body's response to Martian gravity isn't speculation, but mathematical certainty based on our understanding of physiology in altered gravitational environments. Any successful Mars settlement must address these biological realities directly. Fighting gravity's effects. Science demonstrates that fighting gravity's effects requires more than willpower. As astronauts on the International Space Station have discovered, maintaining human physiology in environments with altered gravity demands rigorous intervention. The ISS has become our testing ground for countermeasures that might someday help Mars settlers. But the solutions we've developed so far reveal both promise and profound limitations. The current defense against microgravity's effects centers on intense daily exercise. ISS astronauts use specialized equipment that simulates weightlifting in a gravity-free environment, allowing them to perform crucial resistance exercises targeting major muscle groups and stimulating bone-preserving stress. They also utilize cardiovascular equipment to maintain heart health when the body no longer continuously fights gravity. These exercise protocols represent our best current approach to preserving physical integrity in space. Yet they demand extraordinary time commitments. Like training for an ultramarathon that never ends, ISS astronauts dedicate approximately 2.5 hours daily to counteract gravity's absence. This substantial time investment raises serious questions about long-term Mars missions, where crew members would need to balance physical maintenance against exploration, research, habitat construction, and countless other mission-critical tasks. The exercise countermeasures, while partially effective, offer diminishing returns over extended periods. They slow deterioration but don't halt it completely. Even with religious adherence to exercise protocols, astronauts returning from 6-month ISS missions show measurable physical decline. For Mars settlers facing years or even lifetimes in reduced gravity, the math becomes increasingly problematic. How many hours of each day can reasonably be devoted to simply maintaining basic physical function? Medical science has responded to this challenge by exploring pharmaceutical interventions that might complement physical exercise. Researchers are investigating medications commonly used for osteoporosis treatment on Earth, particularly bisphosphonates, which inhibit the cells responsible for bone resorption. These medications essentially slow the process of calcium being leached from bones, potentially preserving density even in gravity-poor environments. The pharmaceutical approach offers efficiency over exercise alone. A medication regimen requires less time than hours of daily exercise. However, medications bring their own complications, including potential side effects during long-term use and questions about how effectively Earth-developed treatments translate to the unique physiological conditions of Mars habitation. Most importantly, pharmaceutical interventions represent mitigation rather than solution. They slow deterioration rather than preventing it entirely. Imagine stepping into a spinning habitat where your body suddenly feels the familiar pull of gravity. This vision represents perhaps the most promising technological approach, creating artificial gravity itself. Once confined to science fiction, rotating habitats that generate centrifugal force have moved into serious research. Studies have demonstrated impressive results for cardiovascular conditioning, showing that spinning environments can effectively simulate gravitational forces on the human circulatory system. These findings suggest that rotating living quarters could potentially address some of gravity's most damaging effects. However, artificial gravity systems present their own complex challenges. The engineering requirements for creating effective rotating habitats at Mars settlement scale would be enormous. Smaller centrifuges for periodic treatment sessions show promise, but would still require significant time commitments from settlers. Additionally, the transition between artificial gravity environments and Mars natural gravity could potentially cause disorientation and adaptation issues, especially if settlers routinely move between different gravitational fields. Even with perfect centrifugal force simulation, exercise would still be needed for maintaining bone, muscle, and aerobic fitness. The body requires both gravitational force and active resistance to maintain terrestrial conditioning. This suggests that even the most advanced gravity countermeasures would likely need to be combined with exercise regimens, again raising questions about time allocation during Mars settlement. Research into bone density preservation offers another avenue worth exploring. The parallels between space-induced bone loss and terrestrial osteoporosis provide valuable research crossover. However, these treatments were developed for naturally aging populations on Earth, not for otherwise healthy individuals living in permanently altered gravitational environments. The long-term efficacy of such approaches for Mars settlers remains uncertain. The reality emerging from current research is sobering. Maintaining Earth-evolved human physiology on Mars would require a complex, multifaceted approach combining exercise, medication, potentially artificial gravity, and careful monitoring. This regimen would consume significant portions of each settler's day and still might not fully prevent physical deterioration over extended periods. The time commitment alone raises serious questions about settlement viability. Can a functioning society be maintained when every member must spend hours daily just preserving basic physical function? For prospective Mars settlers, daily life would involve a rigorous regimen of exercise, medication, and potentially time in artificial gravity environments, all while attempting to build a functioning society on an inherently hostile planet. The time and resource commitments would be substantial, potentially limiting the productive capacity of early settlements when productivity would be most crucial. This predicament exposes a central paradox in Mars settlement planning. The more effectively we preserve Earth normal physiology, the less time settlers have to actually build and maintain their new civilization. Conversely, accepting greater physical adaptation might increase productive time, but potentially render returning to Earth impossible as bodies become too adapted to Mars conditions. Either approach demands difficult trade-offs with no perfect solution evident in current science. The invisible killer, radiation. While Mars settlers wrestle with gravity's physical demands, an even greater threat silently awaits them, one that can't be countered with exercise or medication. On the Martian surface, radiation levels reach up to 50 times higher than Earth's, equivalent to receiving 10 chest X-rays every single day, with each burst of cosmic particles potentially severing the delicate strands of your DNA. Mars lacks the fundamental safeguards that have protected life on Earth for billions of years. Unlike our planet, Mars possesses no global magnetic field to deflect incoming radiation. Without this invisible shield, the Martian surface lies exposed to the full brunt of space's radioactive bombardment. The thin Martian atmosphere, over 100 times less dense than Earth's, provides minimal additional protection. This combination of vulnerabilities creates an environment where radiation freely reaches the surface, creating hazardous conditions for any unprotected humans. The radiation environment on Mars consists of 3 primary components, each with its own devastating effects. Particles trapped in Earth's magnetic field pose minimal threat on Mars, but the other 2 sources create significant danger. Solar flares periodically erupt from the sun, sending waves of charged particles hurtling through space at near-light speeds. These events are unpredictable and can temporarily spike radiation levels to extreme heights. Even more concerning are galactic cosmic rays, high-energy particles accelerated by distant cosmic events like supernovae. These particles travel at nearly the speed of light and carry enormous energy, making them particularly damaging to living tissue. Like an invisible storm constantly battering the Martian surface, this radiation possesses sufficient energy to strip electrons from atoms, a process called ionization. When this occurs within human cells, it creates unstable molecules called free radicals that trigger chain reactions of cellular damage. Most critically, ionizing radiation directly impacts DNA, the blueprint for all cellular function and reproduction. The biological effects operate on a cellular level, far beyond what human senses can detect. When high-energy particles pass through tissue, they leave trails of ionization that can break the chemical bonds in DNA strands. Single-strand breaks may be repaired by cellular mechanisms, but double-strand breaks, where both sides of the DNA helix are severed, often lead to irreparable damage or faulty repairs. These genetic mutations accumulate over time, potentially leading to cancer when affected cells begin to replicate uncontrollably. This silent enemy works stealthily, creating damage that manifests through both immediate and long-term health effects. Acute radiation syndrome occurs at high doses and can cause nausea, vomiting, and potentially fatal damage to the gastrointestinal tract and central nervous system. While such extreme exposures would be rare on Mars outside of major solar events, the chronic low-dose exposure presents an equally serious concern. The quantitative reality of this exposure is sobering. Research indicates that astronauts on Mars would face effective radiation doses ranging from 50 to 2,000 millisieverts, MSV, depending on location, solar activity, and exposure duration. For perspective, radiation workers on Earth operate under strict annual limits of 50 MSV, while the average person receives approximately 3 MSV per year from natural background sources. Mars settlers would potentially receive the equivalent of 100 to 20,000 chest X-rays annually, with the radiation penetrating deeper and causing more complex damage than medical X-rays. Cancer risk increases significantly with accumulated radiation dose, with studies suggesting Mars settlers would face substantially higher lifetime cancer probability than their Earth-bound counterparts. Beyond cancer, emerging research points to concerning effects on the cardiovascular and central nervous systems. Radiation damage to blood vessels may accelerate atherosclerosis, while neurological impacts could include cognitive impairment and accelerated brain aging. These effects become particularly troubling for long-duration Mars missions or permanent settlement scenarios, where cumulative exposure would continue indefinitely. The radiation damage process illustrates why this threat differs fundamentally from gravity-related challenges. When radiation particles strike DNA molecules, they can cause breaks in DNA strands and loss of DNA bases. If the cell's repair mechanisms fail or make errors during repair, mutations become permanent. Unlike muscle or bone, which can rebuild with proper stimulation, damaged DNA represents a one-way deterioration process. Each mutation slightly increases cancer risk, creating a statistical inevitability of cellular malfunction given sufficient time and exposure. Radiation presents unique challenges for Mars habitation because humans cannot develop natural resistance to it. Evolution has never equipped us with cellular mechanisms to resist space radiation, as Earth's magnetic field and atmosphere have shielded life throughout evolutionary history. Unlike cold adaptation or altitude acclimation, radiation resistance cannot be developed through exposure. Quite the opposite, as exposure only increases cumulative damage. NASA's Human Research Program recognizes radiation as one of the most significant barriers to Mars exploration. Their research focuses on developing countermeasures across multiple fronts. These include shielding materials for vehicles and habitats, pharmaceutical interventions that might offer limited radio protection, and propulsion technologies to reduce transit time between planets. The practical implications for Mars settlers prove daunting. Surface activities would require strict time limitations. Habitat designs would require massive shielding or underground construction, dramatically increasing mission complexity and cost. Even with optimal protective measures, cancer risk would remain significantly elevated, creating ethical questions about acceptable risk thresholds. What makes radiation particularly insidious is its invisibility coupled with delayed effects. Unlike the immediate sensations of low gravity or extreme temperature, radiation damage accumulates silently, potentially manifesting as cancer decades after exposure began. Mars settlers would live with the knowledge that their DNA sustains daily damage that could eventually prove fatal, while never being able to sense the threat directly. The radiation reality forces us to confront an uncomfortable question. Can human biology, fundamentally adapted to Earth's protective environment, ever truly thrive on a planet bathed in cosmic radiation? The answer requires sophisticated protection strategies shielding the human body. The sophisticated protection strategies we're developing for Mars settlers reveal an uncomfortable truth. The difference between a spacecraft's aluminum shield and what humans truly need on the red planet resembles comparing a paper umbrella to a concrete bunker during a cosmic hurricane. As we'll see, the engineering challenges of protecting human life against particles moving at nearly the speed of light forces us to reimagine what Mars habitation might actually look like. Current spacecraft shielding technology faces a fundamental limitation against Mars' radiation environment. Standard aluminum hulls can deflect some radiation, but they're virtually transparent to high-energy galactic cosmic rays. These heavy ions travel at nearly the speed of light, penetrating spacecraft materials and human tissue with devastating efficiency. The physics problem is straightforward, but nearly impossible to solve. How do you stop particles moving at relativistic speeds without creating shields so massive they become impractical to transport to Mars? The limitations of traditional shielding become more apparent when considering the practicalities of Mars missions. Every kilogram of shielding material requires fuel for transport, creating a compounding problem. Engineers must balance protection against launch costs and payload constraints. This balance typically results in compromises that leave crews vulnerable to radiation exposure over extended Mars missions. While spacecraft can incorporate strategic shielding around sleeping quarters and high-occupancy areas, complete protection using conventional materials remains elusive. Fortunately, several promising materials offer potential solutions to this radiation challenge. Water serves dual purposes in spacecraft and habitat design. Its hydrogen content makes it remarkably effective at absorbing radiation, particularly neutrons produced when cosmic rays interact with spacecraft materials. Future habitat designs could incorporate water tanks strategically positioned to shield living quarters. A water barrier 40 centimeters thick can significantly reduce radiation exposure, while simultaneously providing a critical resource for the settlement. Martian regolith, the loose soil and rocky material covering the planet's surface, offers an even more promising local resource for radiation protection. Unlike water, it doesn't need to be transported from Earth. Studies suggest that approximately 3 meters of packed Martian soil would provide radiation protection comparable to Earth's atmosphere. Habitat designs could incorporate regolith-filled walls or be covered entirely with soil gathered and moved by autonomous robots before human arrival. This dirt shield approach represents one of the most practical near-term solutions for surface habitation. Despite these material solutions, significant challenges remain. The process of collecting and using regolith requires energy and machinery. The fine, abrasive nature of Martian dust presents contamination challenges. Additionally, habitats designed to support the weight of 3-meter soil shields require substantially stronger structural elements, increasing construction complexity. Underground habitats offer perhaps the most effective radiation protection strategy, taking advantage of natural shielding provided by Mars itself. By establishing settlements within caves, lava tubes, or excavated tunnels, settlers gain the equivalent of unlimited regolith protection without the construction challenges of surface buildings. Radar investigations have already identified potential lava tubes on Mars that could house entire communities protected from radiation and other surface hazards. The underground approach fundamentally changes our vision of Mars settlement from the typical science fiction depiction of geodesic domes on the surface to something resembling ant colonies with limited surface exposure. While practical from a radiation perspective, this underground existence creates profound psychological and operational challenges. Humans evolved under open skies, and extended subsurface living could trigger claustrophobia, disrupted circadian rhythms, and other psychological strains. For necessary surface activities, specialized spacesuits with enhanced radiation protection will be essential. Current spacesuit technology offers minimal radiation shielding, designed primarily for shorter duration activities. Mars explorers would need next-generation suits incorporating hydrogenated materials and potentially active radiation detection systems that could alert wearers to increasing exposure levels. However, truly effective radiation shielding adds weight, limiting mobility and extending already complex surface operations. The challenge extends beyond materials science into biology and medicine. Researchers are investigating radioprotectants, compounds that can shield cells from radiation damage or accelerate repair mechanisms. These range from antioxidants that neutralize radiation-generated free radicals to more sophisticated agents that enhance DNA repair mechanisms. Some compounds show promise in laboratory settings, potentially reducing radiation damage by 30 to 40% when administered before exposure. Biological interventions face significant hurdles before implementation on Mars missions. Most radioprotectant compounds require administration shortly before radiation exposure, making them impractical for continuous exposure scenarios. Others show concerning side effects during long-term use. The most promising approaches combine multiple protection strategies, physical shielding, habitat design, and biological interventions to create defense in depth against the radiation threat. When we assess these protection strategies, a sobering reality emerges. The most effective approach will likely involve establishing primarily subterranean habitats with heavily shielded transportation systems between them. Surface activities would be strictly limited to essential operations, conducted by personnel tracked for cumulative exposure and rotated to minimize individual risk. This radiation reality raises profound questions about Mars settlement itself. If humans must spend the majority of their time underground to avoid dangerous radiation exposure, can we truly claim to be living on Mars rather than merely living in Mars? The distinction matters both philosophically and practically for mission planning and settler psychology. The vision of expansive Martian vistas and surface exploration that motivates many Mars enthusiasts may be limited to brief, carefully managed excursions from underground havens. Some researchers explore more speculative solutions, like generating an artificial magnetic field around Mars settlements or bioengineering approaches to enhance radiation resistance. Both remain theoretical, requiring technological breakthroughs and raising profound ethical questions about human adaptation to the harsh Martian environment. Thermal extremes and human limits. Earth's biological thermostat has evolved over millions of years to function within a relatively narrow temperature range. But what happens when we transplant our finely tuned bodies to a world where extreme temperature shifts occur seasonally, and even between breakfast and dinner? Beyond radiation's invisible threat lies an environmental challenge you'd feel within moments of exposure. Mars presents a thermal environment utterly alien to human physiology. While Earth's atmosphere acts as a thermal blanket, maintaining relatively stable temperatures, Mars offers no comfort. Its atmosphere, a wispy fraction of Earth's, allows heat to escape with alarming efficiency, creating temperature fluctuations that would overwhelm our biological temperature regulation systems. The numbers tell a stark story. With an average temperature of minus 60 degrees Celsius, Mars functions like a world with a broken thermostat. At the equator, during midday, temperatures can reach a seemingly pleasant 20 degrees Celsius, comparable to a mild spring day on Earth. By nightfall, however, the same location plummets to minus 73 degrees Celsius. This 93-degree swing would be comparable to experiencing pleasant afternoon weather in Madrid, Spain, followed by conditions colder than Antarctica's most brutal winter, all within hours. These rapid extremes make Mars particularly dangerous. The human body can acclimate to different climates over time. People live in both Saudi Arabian deserts and Siberian tundra, but our physiology cannot handle rapid temperature shifts of such magnitude. Our thermoregulatory system maintains core body temperature at approximately 37 degrees Celsius through a complex interplay of physiological mechanisms, including sweating, shivering, and vascular constriction or dilation. This system evolved for Earth's relatively moderate conditions and becomes overwhelmed by rapid, extreme changes. Near the Martian poles, conditions worsen dramatically. Winter temperatures can plunge to minus 125 degrees Celsius. cold enough to freeze carbon dioxide from the atmosphere into solid dry ice. A human exposed to such conditions without protection would experience catastrophic tissue damage within seconds. At these temperatures, exposed skin freezes almost instantly. The water in cells crystallizes, rupturing cell membranes and causing permanent damage. Blood vessels constrict severely in an attempt to preserve core body heat, cutting off circulation to extremities, leading to frostbite and tissue death. This extreme cold is immediately life-threatening. Hypothermia sets in when core body temperature drops below 35 degrees Celsius, impairing cognitive function and motor control. Below 32 degrees Celsius, cardiac arrhythmias develop and death becomes imminent. On Mars, without substantial protection, this process would occur with alarming speed due to the environment's efficiency at drawing heat from the body. Even the warm periods on Mars are deceptive. The thin atmosphere means that while direct sunlight might heat surface materials, any shade creates immediate cold zones. You could literally stand with one foot in relatively comfortable temperatures and the other in freezing conditions. This creates a thermal patchwork across the landscape that makes consistent temperature management nearly impossible. The thin Martian atmosphere compounds these challenges. On Earth, our atmosphere serves as an insulating blanket, distributing heat and moderating temperature swings. Mars lacks this buffering effect. Heat transfer through convection becomes far less efficient in the thin carbon dioxide atmosphere, making both heating and cooling systems less effective and requiring substantially more energy than comparable systems on Earth. These thermal realities create an engineering nightmare for Martian habitats. Structures must be extraordinarily well insulated, essentially functioning as thermos bottles to maintain internal temperatures. The energy requirements for heating would be substantial, particularly during frigid nights. Solar power, abundant during daylight, becomes unavailable during dust storms lasting weeks or months. This necessitates massive energy storage systems or alternative power sources like nuclear generators, adding complexity, weight, and cost to Mars habitation plans. Venturing outside presents additional challenges. Spacesuits must balance insulation against cold while preventing overheating during physical activity. In Mars' thin atmosphere, convective cooling becomes ineffective, forcing cooling systems to rely on radiation and conduction. This requires active cooling systems that add weight and power requirements to suit designs. Energy consumption for temperature regulation would constantly concern Mars settlers. Every bit of energy used for heating or cooling becomes unavailable for oxygen generation, water purification, or communications. These thermal challenges would limit time outside habitats and constrain exploration potential to brief excursions during moderate temperature periods. Equipment operation becomes equally complex. Tools must function across extreme temperature ranges as materials expand and contract at different rates, creating mechanical stress. Electronic components have operating ranges frequently exceeded on Mars. Even simple tasks bring risks. A metal tool left in sunlight might become hot enough to burn through gloves. The psychological impact of thermal constraints adds another dimension. Confinement to habitats due to external temperature extremes creates experiences similar to polar stations on Earth, where personnel develop cabin fever. Unlike Antarctic researchers anticipating warmer seasons, Mars settlers would face these constraints permanently. Some engineers propose partial solutions, like underground habitat networks utilizing Mars' relatively stable subsurface temperatures. Below about 1 meter of soil, temperatures remain fairly constant, offering protection from radiation and thermal extremes. However, this approach limits direct interaction with the Martian environment, essentially forcing humans to become subsurface dwellers rather than explorers. Managing Mars' thermal environment demands substantial technology. Habitats would require multiple redundant heating and cooling systems with energy consumption dwarfing Earth structures. Spacesuit design would need significant advancement, potentially using phase change materials and more efficient cooling systems. Surface vehicles would require specialized thermal management to protect occupants and components, adding layers of complexity to an already challenging Martian existence. The air we can't breathe. Beyond the challenge of thermal management lies an even more immediate threat that no amount of technology can let us ignore: Mars' atmosphere itself. At just 6.35 millibars of pressure compared to Earth's 1,013, and composed of 95.32% carbon dioxide with virtually no oxygen, the Martian air is actively hostile to human physiology in ways that fundamentally alter survival requirements. To understand the severity of this threat, consider that every breath you take on Earth contains approximately 210,000 times more oxygen molecules than the same volume on Mars. The Martian atmosphere contains a mere 0.13% oxygen, compared to Earth's life-sustaining 21%. This creates an environment where our respiratory system would catastrophically fail. The human body has evolved specific requirements for atmospheric pressure and composition that Mars violates in every respect. Our lungs function through pressure differentials that allow oxygen to diffuse across the alveolar membrane into our bloodstream. When that pressure differential disappears, as it would in Mars' thin atmosphere, this life-critical exchange stops completely. The oxygen present is insufficient both in percentage and absolute quantity due to the extremely low pressure. Exposure to Mars' atmosphere would produce severe effects beyond simple suffocation. The 95.32% carbon dioxide concentration would trigger immediate carbon dioxide poisoning. Your respiratory center would detect dangerously high CO2 and frantically signal for increased breathing rate, creating an overwhelming sensation of suffocation even as you gasp futilely for air. Perhaps the most dramatic effect would come from the near-vacuum conditions. At less than 1% of Earth's pressure, the physics of how fluids behave changes dramatically. A phenomenon called ebulism would occur, where the dramatically lower atmospheric pressure causes bodily fluids to vaporize. The moisture in your eyes, mouth, and airways would immediately begin to boil at body temperature. This occurs when pressure drops below what's called the Armstrong limit, approximately 6.3 kilopascals, a threshold Mars sits below. Stepping onto Mars without protection would be like entering an alien, suffocating bubble where your body's chemistry betrays you. Your blood begins to boil, your lungs collapse, and consciousness fades within seconds. Death would follow quickly from a combination of asphyxiation, carbon dioxide poisoning, and the catastrophic physiological damage from ebulism. This stark reality means that any human presence on Mars requires creating completely artificial atmospheres, essentially bringing tiny pieces of Earth's environment with us. These life support systems must operate with absolute reliability, as even brief failures could prove fatal within minutes. Creating habitable environments on Mars means engineering closed systems that maintain Earth-like atmospheric pressure, approximately 101 kilopascals, oxygen levels around 21%, and eliminate excess carbon dioxide, while controlling temperature and humidity. These systems must operate continuously, never dropping below critical thresholds regardless of external conditions. Generating oxygen becomes a fundamental challenge for long-term Mars habitation. NASA's MOXIE experiment aboard the Perseverance rover offers promise by successfully demonstrating oxygen production from the Martian atmosphere. This technology electrochemically splits carbon dioxide molecules to extract oxygen, providing a pathway toward using Mars' own resources to sustain human life. While encouraging, scaling this technology to support human settlements would require substantial energy resources and redundant systems. A full-scale oxygen generation system for a small Mars colony would need to produce hundreds of times what MOXIE has demonstrated, requiring significant power infrastructure. This represents one of the most critical engineering challenges for Mars settlement, as oxygen production must continue without interruption. Maintaining atmospheric pressure presents another substantial hurdle. Every airlock cycle and microscopic leak represents a pathway for precious atmosphere to escape. Mars habitats would require spacecraft-grade engineering throughout their construction. The mass penalty for this level of engineering means habitats would likely be modular and limited in size, creating confined living spaces. Detecting and repairing leaks becomes a constant priority, as even small breaches could deplete oxygen reserves or cause dangerous pressure drops. Maintenance systems would need continuous monitoring of atmospheric composition, with redundant sensors and emergency protocols. The Martian atmosphere introduces additional complications through its dust content. The fine iron oxide dust can infiltrate mechanical systems, clog filters, and potentially carry unknown chemical compounds that might react with habitat materials. The regular dust storms, which can become planet-encircling events lasting months, would further stress external components and reduce solar power generation. This atmospheric reality creates a psychological burden unlike any on Earth. Every Martian settler would live with the knowledge that their survival depends entirely on mechanical systems, with death literally waiting just beyond the habitat walls. Each venture outside would require complex preparation with spacesuits that function as miniature life support systems. The resource requirements for maintaining breathable environments create a cascading series of engineering challenges. Oxygen production depends on reliable power generation. Power systems require maintenance and replacement components. Backup systems need their own independent power sources. Mars settlements would need extensive redundancy far beyond what we typically engineer for Earth-based applications. Unlike temperature extremes or radiation, which might be managed with passive systems, atmospheric management requires active, energy-intensive processes that cannot be interrupted. Even sleep becomes a calculated risk, dependent on reliable alarms and automatic responses to atmospheric anomalies. With proper life support systems, humans could survive indefinitely on Mars, but the margin for error would be measured in minutes rather than days. The technology to create sustainable atmospheres exists in principle, but requires significant scaling and reliability improvements before long-term Mars habitation becomes feasible. The mind on Mars. Technology may solve the atmosphere challenges, but beneath the surface of every Mars mission plan lies a more elusive threat. The psychological burden of extreme isolation in an environment actively hostile to human life. Research from Space Analog shows that even the most meticulously selected crews experience profound mental changes when the Earth is just a pale blue the effect takes hold. Unlike physical challenges that can be measured and engineered against, the human mind presents a complex battlefield when confronted with the Martian reality. Living where the barrier between life and death is measured in millimeters of habitat material creates existential stress unknown on Earth. The Mars 500 program offered our first substantial glimpse into these psychological realities. 6 volunteers spent 520 days sealed in a Moscow facility, simulating a Mars mission's duration. They celebrated birthdays in isolation, created routines to stay sane, and even staged a mock Mars landing. While the crew accomplished mission goals with high work autonomy, troubling patterns emerged. As weeks turned to months, the crew exhibited increasing homogeneity in values and became reluctant to express negative feelings, a shift toward groupthink that could compromise critical decision-making on Mars. Crew members reported progressive increases in loneliness and perceived lower support from colleagues as the mission continued. This deterioration occurred despite careful selection and preparation, and without the actual mortal danger Mars settlers would face daily. The psychological hurdles compound when considering the disappearing Earth phenomenon. As Earth shrinks to a mere dot in the heavens, astronauts experience separation unlike anything in human history. Mission planners have suggested countermeasures like telescopes or virtual reality experiences of Earth. Yet these create a paradox. They might alleviate homesickness while deepening depression as crew members reflect on what they've left behind. Communication delays transform human connection fundamentally. Mars settlers would endure delays ranging from 4 to 24 minutes each way. Imagine speaking to a loved one during a personal crisis and waiting nearly an hour for their response. No spontaneous laughter. No immediate comfort. The calm delay assessment investigation confirmed these impacts, showing significant increases in stress and frustration alongside reductions in teamwork. During emergencies, Mars settlers would face the added burden of managing without immediate guidance from Earth, alone in their decision-making when stakes are highest. Confined living spaces add another layer of psychological pressure. Step outside impulsively during an argument, death within minutes. Feeling claustrophobic? The only alternative is a lethal environment. This spatial constraint creates a pressure cooker that Earth-based analogs struggle to truly replicate. The constant awareness of life support dependency creates what psychologists call a perpetual low-grade trauma state. Every unusual sound from machinery becomes cause for alarm. Every temperature fluctuation prompts stress responses. Mars settlers would develop hypervigilance toward environmental factors that Earth dwellers process unconsciously, draining cognitive resources and emotional reserves over time. Circadian disruption intensifies these challenges. The Martian day is approximately 40 minutes longer than Earth's. The human body's biological clock has evolved over millions of years to match Earth's precise 24-hour cycle. Studies from polar research stations demonstrate that even slight circadian misalignment leads to sleep disturbances, mood disorders, and cognitive impairment. Mars settlers would continuously battle their internal timing mechanisms. NASA's Human Research Program has begun investigating countermeasures. Learning new skills appears to ward off depression among isolated crews. During analog missions, participants who mastered new languages or medical procedures reported higher satisfaction levels. Similarly, tending to plants offers benefits beyond fresh food. The psychological comfort of nurturing living things in a sterile environment provides profound emotional value. Virtual reality presents another therapeutic avenue. The European Space Agency's VR mental care project tests how immersive natural environments can improve psychological well-being during missions. Early results suggest these virtual escapes help manage stress and anxiety. The no-return reality presents unprecedented mental challenges. Unlike any previous human exploration, Mars settlers face the possibility of a one-way journey. Knowing emergency evacuation is impossible creates a psychological framework humanity has never encountered. This reality changes everything. Leadership dynamics take on heightened importance under these conditions. Research reveals that crew members often displace tension onto mission control as a coping mechanism. The commander's support role strongly correlates with group cohesion, suggesting leadership selection may be as crucial as technical qualifications. During one Antarctic winter-over mission, the station leader's inclusive decision-making style prevented serious conflicts despite extreme isolation and confinement. The post-mission phase raises questions rarely addressed in planning. What psychological effects might manifest after years on Mars? What strategies might support rehabilitation upon return? These questions remain largely unanswered. High autonomy requirements would fundamentally alter how settlers approach self-care. With minimal external oversight, they would shoulder increased responsibility for maintaining psychological well-being. Current research shows significant gaps in understanding how astronauts manage themselves during actual space missions. The evidence suggests Mars habitation requires a fundamental shift in mental health support for space explorers. Traditional models of periodic evaluations would prove inadequate for the complex, prolonged stressors of Mars living. Systems incorporating continuous monitoring, peer support training, and biological adaptation possibilities. While psychological countermeasures might help Mars settlers maintain mental equilibrium, a more fundamental question emerges. Could the human body itself eventually adapt to the red planet's harsh conditions? Evolution has equipped humans with remarkable adaptability, allowing us to inhabit nearly every environment on Earth. But Mars presents challenges beyond anything in our evolutionary history. Natural selection, the process that drives evolution, works through subtle advantages that accumulate over time. Earth's evolutionary pressures shaped our bodies for 300,000 years of human existence, fine-tuning us specifically for this planet's gravity, radiation levels, atmospheric composition, and temperature ranges. Consider the Himalayan populations who developed enhanced oxygen processing abilities at high altitudes. These adaptations include increased lung capacity, altered blood chemistry, and more efficient oxygen transport systems. After approximately 3,000 years of natural selection, Tibetans can thrive in environments with oxygen levels 40% lower than sea level. Similarly, Andean populations developed larger chest capacities and higher red blood cell counts to cope with their mountainous habitat. Mars, however, presents simultaneous challenges far more extreme than Earth's harshest environments. The adaptation gap becomes clear when comparing Earth's high-altitude regions to Mars conditions. While Tibetans adapted to oxygen at 60% of sea level concentrations, Mars' atmosphere contains less than 1% of Earth's pressure with virtually no oxygen. This represents a fundamental difference rather than a more extreme version of the same challenge. What makes Mars particularly challenging is that many of its conditions present binary survival thresholds rather than gradients along which adaptation can occur incrementally. The human respiratory system requires a minimum partial pressure of oxygen to function. Below certain thresholds, oxygen simply cannot transfer to the bloodstream regardless of evolutionary adaptations. The pressure gradient necessary for respiration is a physical requirement based on gas exchange principles. Similarly, the absence of a global magnetic field on Mars means surface exposure to radiation levels that can damage DNA and increase cancer risk substantially. Natural selection might eventually favor individuals with slightly better DNA repair mechanisms, but the protection would be marginal compared to the magnitude of the threat. Humans have evolved on Earth for hundreds of thousands of years, yet we still haven't developed natural defenses against many Earth-based radiation sources. In reduced gravity, over many generations, natural selection might favor individuals whose bones and muscles maintain better structural integrity with less gravitational stress. The musculoskeletal system shows remarkable plasticity, responding to different loading conditions throughout life. However, these adaptations represent optimizations within Earth's environmental range, not fundamental rewiring of human physiology. Artificial selection, deliberately selecting for advantageous traits, could potentially accelerate adaptation. This approach involves identifying individuals with characteristics beneficial for Mars conditions and encouraging reproduction. However, this raises profound ethical questions and practical limitations. The effectiveness of artificial selection depends on existing genetic diversity, and many traits critical for Mars survival likely don't exist in the current human gene pool. The limitations of natural adaptation don't mean that humans couldn't survive on Mars. They indicate that technology, rather than biology, must bridge the gap. Habitats, spacesuits, and other protective systems would remain necessary regardless of how long humans live there. Natural adaptation might eventually help humans better tolerate the 38% gravity, but it wouldn't eliminate the need for radiation shielding or pressurized environments. If humans established a permanent, self-sustaining colony on Mars with limited return to Earth, genetic drift would likely begin to create a distinct population over generations. Initially, these differences would be subtle, perhaps slightly different bone structures or cardiovascular systems optimized for lower gravity. Over thousands of years, assuming continued isolation, these differences could accumulate until Mars-born humans might struggle to readapt to Earth conditions. This potential divergence raises profound questions about human identity and the possibility of speciation as we spread throughout the solar system. Would Mars colonists eventually evolve into a separate species given enough time and isolation? The possibility exists, though the time frame extends far beyond our current planning horizons. The immediate solution to Mars' environmental challenges lies not in waiting for natural adaptation, but in directly intervening. In human biology, Genetic engineering technologies like CRISPR offer theoretical pathways to enhance human capabilities beyond what natural selection could achieve. These approaches could potentially target specific adaptations needed for Mars: radiation resistance, improved bone density maintenance, enhanced oxygen utilization, and modified cardiovascular function for the lower gravity environment. However, significant technical and ethical barriers still stand before such modifications could be safely implemented. The long-term consequences of genetic alterations remain largely unknown, and unexpected effects could emerge over generations. The complexity of the human genome means that modifications intended to address one challenge might create vulnerabilities in other systems. The gap between what we can imagine and what our biology permits represents the fundamental challenge of becoming a multi-planetary species. Technologies that protect humans from Mars' environment will remain essential indefinitely, underscoring the necessity of engineering solutions rather than biological ones. Engineering humans for Mars. Technology may shield our bodies from Mars hostility, but what if our bodies themselves could become the technology? The revolutionary gene editing tool CRISPR-Cas9 represents a paradigm shift in our approach to Mars colonization. Unlike previous sections where we explored how to protect humans from the Martian environment, genetic engineering invites us to consider a more fundamental question. Could we redesign ourselves to thrive where evolution never prepared us to survive? CRISPR-Cas9 has transformed genetic modification from science fiction into scientific reality. This molecular scalpel allows precise alterations to the genome, targeting specific DNA sequences with unprecedented accuracy. Such precision opens fascinating possibilities for enhancing human capabilities specifically for Mars conditions. This power comes with significant limitations. Among the most concerning are off-target effects, where CRISPR machinery unintentionally modifies genes other than those targeted. These unplanned edits could trigger cascading health consequences that might not become apparent for generations. These modifications would potentially create genetic changes that pass to descendants, with all the unforeseen complications that might entail. Radiation resistance represents one of the most promising applications of genetic engineering for Mars adaptation. Radiation poses an existential threat to Mars settlers, but certain organisms on Earth have evolved remarkable resilience. The bacterium Deinococcus radiodurans stands as nature's supreme radiation survivor, capable of withstanding radiation doses 1,000 times what would kill a human. Scientists are investigating the genetic basis of this extraordinary resilience. Deinococcus radiodurans possesses highly efficient DNA repair mechanisms that allow it to restore damaged genetic material with remarkable efficiency. In theory, we could incorporate genes responsible for these repair mechanisms into human cells, enhancing our ability to withstand constant radiation bombardment on Mars. Imagine a Mars settler like Elena, born in 2050, working outside her habitat for hours without concern about cumulative radiation damage. Her cells continuously repair radiation-induced DNA breaks, similar to how self-healing materials automatically fix microcracks. The implications extend beyond space travel. Such modifications could reduce cancer risk and slow aging processes even on Earth. Another critical challenge is maintaining bone density in Mars' reduced gravity. On Earth, our skeleton constantly rebuilds itself in response to gravitational stress, but this process falters in low-gravity environments. Genetic engineering could intervene by modifying genes involved in bone formation and maintenance. Scientists are researching ways to enhance the activity of genes promoting osteoblast function, cells responsible for building new bone tissue, while suppressing genes triggering bone breakdown. This balance could be adjusted to favor bone preservation even when gravitational signals diminish. The objective would be creating a modified bone maintenance system that remains robust despite receiving weaker gravitational cues, much like upgrading a car suspension system to perform optimally on different terrain. Oxygen utilization represents another frontier for potential genetic enhancement. While we can't change Mars' thin carbon dioxide atmosphere, We might improve how efficiently our bodies use limited oxygen available in artificial habitats. Genetic modifications could enhance oxygen uptake, improve transport through the bloodstream, and optimize cellular utilization. This might involve modifications to hemoglobin structure to increase oxygen binding capacity or enhancement of mitochondrial efficiency. Such changes would be crucial in environments where atmospheric resources must be carefully managed, comparable to upgrading an engine to run efficiently on limited fuel. Synthetic biology takes genetic engineering further by designing entirely new biological pathways specifically adapted for Martian conditions. This could involve engineering organisms with metabolic pathways that don't exist in nature. Settlers might have enhanced abilities to produce essential vitamins their bodies cannot naturally synthesize, reducing dependency on nutritional supplements. Engineered symbiotic relationships with microorganisms could help process Martian resources. Synthetic biology might even create organisms capable of transforming Martian atmospheric components into breathable air or useful compounds, effectively turning biology into infrastructure. However, the time frame for developing these technologies exceeds current Mars mission planning windows. While CRISPR has advanced rapidly, safely engineering complex traits in humans remains in its infancy. Current research primarily focuses on correcting single gene disorders, a far simpler challenge than engineering complex adaptive traits for extraterrestrial environments. Developing safe genetic modifications would require extensive research phases spanning decades. The most optimistic estimates suggest preliminary human applications might begin in the 2040s, likely limited to therapeutic rather than enhancement purposes. The ethical considerations surrounding human genetic engineering add another layer of complexity. Society must confront difficult questions about consent, equity, and the very definition of humanity. Who decides which modifications are permissible? Would genetically enhanced Mars settlers constitute a new branch of humanity? Modifications that provide advantages on Mars might create disadvantages if individuals or their descendants return to Earth. The human genome represents an intricate system developed through millions of years of evolution. Alterations made for specific environments could ripple through this system unpredictably. How would genetically modified individuals view themselves and relate to unmodified humans? Will we create a two-tiered species, potentially leading to discrimination? These questions extend far beyond technical feasibility into ethics, philosophy, and human rights. Despite these challenges, genetic engineering remains one of the most promising long-term approaches to enabling sustainable human presence beyond Earth. Unlike mechanical life support systems that can fail catastrophically, genetic adaptations would become intrinsic to the organism, providing continuous protection without external power requirements or maintenance needs. Throughout our exploration of space, we've often imagined conquering other worlds. But as we've seen, the reality is more nuanced. Our bodies, these remarkable machines, evolved over millions of years on Earth, face profound challenges beyond our home planet. The path forward requires harmony between our biology and alien environments. This means developing technologies that complement our evolutionary heritage, advanced shielding, closed-loop life support systems, and perhaps careful genetic modifications. Our success depends on this delicate equilibrium. The question becomes about maintaining our essential humanity while adapting to worlds our ancestors never imagined. Can we preserve what makes us human while evolving to meet the